morning everyone. Today we are going to see Operating System Unit 4 Session 4. In today's session we are going to study about non-contiguous memory allocation. So non-contiguous memory allocation is whenever you are going to bring the processes from secondary memory to main memory for execution. So that process can be placed anywhere in the main memory. So wherever there is a memory left in the partitions or the blocks, as you all know that main memory is divided into blocks and partitions. So wherever the memory is left in one of the partitions anywhere, so there that process will be placed. So the memory utilization is proper good here in a non-contiguous memory allocation. So wherever there is a memory left over in the partitions, blocks, there that process can be placed for execution. So in this, when a process is moved from secondary memory to main memory, it can be divided into pieces and placed in main memory. That process data is divided into pieces, different process, different memory size, and it is placed in the main memory. So advantage of non-contiguous memory allocation is that it will not suffer from external fragmentation. We already studied about internal fragmentation and external fragmentation. Internal fragmentation is what? When you allocate a process in a particular block of main memory, and then the remaining memory which is going to be waste, it cannot be allocated to any other process. So one block, only one process can be allocated, and remaining memory, if that process size is small compared to the block, then remaining memory is going to be waste, and that we call it as internal fragmentation. External fragmentation is what? The memory is available in the main memory. Still there is a space left over. And if the process comes with less size, but you cannot allocate the memory, that we call it as external fragmentation. See in this example, this is a partition, one block. So from this block, 2 KB memory has been allocated. So this memory indicates this 2 KB memory has been allocated. And this side there is a 4 KB left, and this side also there is a 4 KB left. So total there is a 8 KB memory left in a block. And if a process comes with 5 KB, then but you cannot allocate it to the process. Still the memory is there in the partition. You can see here 8 KB memory is there, and you cannot allocate the process. 5 KB process you cannot allocate because it is not in a contiguous form. So the memory which is there here, some of the memory you can find out this side, some of the memory is this side. It is not in a contiguous manner, one by one. So even if you have 8 KB free space, but that 8 KB space is not contiguous, that's why you cannot place 5 KB data in the memory. And this problem we call it as external fragmentation. So this problem can be solved in a non-contiguous memory allocation because so whenever you are going to bring the processes in the main memory, it can be placed anywhere in the blocks. So 5 KB process has come. So 4 KB you can allocate here. Process you can allocate here. 4 KB process. And remaining 1 KB you can allocate in this. So it has utilized the memory properly here. 4 KB was allocated from this process, from this block, and remaining 1 KB from this block. So the process has been placed in the memory for execution. So this non-contiguous memory can be implemented in the operating system in various ways using the linked list, using pointers, paging, segmentation, and so on. So first we'll see linked list using pointers technique. So how using linked list, this contiguous memory, non-contiguous memory allocation is implemented in a operating system. So data can be accessed with help of pointers in form of linked list. So whenever process is brought up from secondary memory to main memory, then anywhere that data can be placed in the main memory, and those will be placed in the various blocks, and in which block that memory is placed, those are linked using the pointers. Now suppose there is a process P1. Now process P1 has brought up from secondary memory to main memory. Some of the data of process P1 is in first block, or some of the data is in some another block, like this way. So that data of that process can be placed anywhere wherever there is a memory. So this data is linked to each other in a form of linked list. So the address of another data of process P1 is linked here, and then the address of another data which is placed in the memory is linked here. So wherever they are placed, so these all data of that process P1 are linked to each other. So if you want to access the last record here, if you want to access this last record, then first of all you need to access all previous block. First of all you need to access all previous data of that process. So first you need to access this data, then you will get the address of next node. Then you will get the address of next node. So like this way, one node will give the address of next node, and then you can reach to the node which you want to access. So randomly you cannot access any data. Suppose if you want to access the last data only, then you cannot access this last data. All the previous data you need to access, and then only you can visit the last node. So first node gives the address of next node, and the procedure continues till we get the needed data. Data can be accessed in one by one fashion. So step by step the data is in a sequential manner, data is accessed. In linear manner the data is accessed. It is one after the other. Randomly any data we cannot access directly. We cannot access data randomly. Does not suffers from external fragmentation. So linked list, using linked list pointers, it does not suffer from external fragmentation. See, wherever there is a memory available, that process is placed anywhere. So it does not suffer from external fragmentation. Disadvantage of this is that accessing elements will be very slow because of accessing elements in linear fashion one by one after. That means whenever you are going to execute this, it is going to be slow because those are linked to each other. So if you want to access the last record, then all previous records you need to access. So that's why it is going to be little slow. Another technique which is used for implementing non-contiguous memory in operating system, paging. So in a paging, secondary memory is divided into equal size of partition called pages. So there is a secondary memory, and that memory is divided into equal size of partitions, and all partitions are of same size, and this we call it as pages. These partitions we call it as pages. Main memory is also divided into same size of partition but called frames. So whatever the partitions are made in secondary memory, same partitions are also made in main memory, and that is also of equal size, but these are called as frames of main memory. Pages can be anywhere in the memory and in any frames. So as processes has to be brought up from secondary memory to main memory. So this, suppose now there is a process P1 and it is stored in, it has taken 3 pages, page 1, page 2 and page 3. So whenever you are going to bring it from secondary to main memory, it can be placed anywhere in the frames. So page 1 you can find out here, page 2 can be in any other frame, and page 3 can be in any other frame. So wherever there is a free partition, there these pages will be loaded in the main memory. So pages can be anywhere in the main memory wherever there is a free space and in any frames. So one process can have many pages where that data will be stored, and all those pages will be brought up to the main memory for execution, and these pages can be placed anywhere in the main memory. Page table for every process is maintained. So how to understand the information for the operating system? Which page is stored in which partition? So the operating system should know this, and this information is maintained in a page table. Now suppose there are 3 processes, then for these 3 processes there are different page tables. So whenever these three processes are there in the main memory for execution, which process information is stored in which frames, which process page is stored in which frame. So these are all information you can find out from page table. CPU generates two parts, page number and offset. So in the contiguous memory allocation we have seen, CPU generates only the one address there, that is instruction number which it wants to execute. Now in this, the CPU generates two parts. One is the page number and offset, and it creates the logical address. And then that logical address will be translated into physical address for execution. You can see here address translator scheme in paging. Address generated by CPU is divided into page number and page offset. Page offset is nothing but which instruction number the CPU wants to execute. Now suppose you can see here, this is the secondary memory where all pages are stored, and suppose this pages is of process, this page is of process P1 and this page is of process P2. Similarly, this pages belongs to process P3, and this pages, now suppose P1 has to be executed, then these two pages has to be brought up to the main memory for execution, and it can be placed anywhere, whichever the frame is empty, there that page can be placed, like page 1 and page 2. So in frame number 2 page 1 is placed, in frame number 3 page 2 is placed. And as I told you, there is a page table also. With every process there is a page table. So this is the pages which are there in the secondary memory, that we call it as logical memory. Now you can see this is a page table of a particular process, and this is the physical memory, main memory, where these pages are placed. You can see here page 0 is placed in frame number 1. You can see here, this information will get here. In frame number 1, which page is there? See here, page 0 is present in frame number 1, and page 2 is present in frame number 3. You can see here, in frame number 3 you can find out page number 2. Similarly, page 3 is in frame number 7. So page, you can see this information, page 3 is in frame number 7. So like this way the information is stored. We also call this as index numbers. We also called as index number of those pages. And this is the address translation architecture in paging. Now how we have translated the addresses in a contiguous memory, like whenever the CPU wants to execute in an instruction number, that will be compared with limit register value, and if it is less, then it will be added with the base address which is present in the relocation address, and then instruction number and base address will be added, and then you will get the physical address in a contiguous memory. Now in a non-contiguous memory, the CPU generates here two parts. One is the page number and other is the instruction number which he wants to execute. Take the example of a book. In a book we find equal size of pages. So it's very easy to maintain. Suppose if there are unequal pages in a book, then it is very difficult to maintain. So in a book we find out equal pages. Now if I tell go to the page number 50 and to a particular instruction or particular topic, then we can easily directly go to the page number and that particular topic. So like this way the CPU, it will instruct, okay, which CPU will instruct which instruction it wants to execute from which page number and which is the instruction number. The CPU will tell this information, then it will refer the page table for it. In a page table, that pages will be stored in which frame. in which frame that pages are stored, that address will be taken. That address we call it as base address. Base address, we also call it as offset. We also call it as, not offset, frame base address. You can see that is stored in this, that base address, and it will added with the instruction number, and then the physical address will be generated, and then it will execute. It will find out the page in the main memory where it is placed, and then it will execute it. So for execution, the CPU will tell which page number it wants to execute and which instruction number, and that information will be found out in the page table, and from this you will get the address of that frame where it is stored, and then that will get added with the instruction number and physical address is generated. You can see here this is one program, and this program is divided into 4 pages. Page 1, so always the page number starts from 0, page 0, 1, 2 and 3. So this program is stored in 4 pages, and these pages now has to be brought up in main memory for execution, and these we call it as frames. These are frames, and these pages can be placed anywhere in this frame. It can occupy any frames for execution. Now you can see the pages are already placed in the frames. You can see these are the pages, 4 pages which are placed in the frames, and which frame, which page is in which frame, this information you will get from page table. In the page table we have 2 columns. One is the page number and one is the frame number. So from this we will understand page 0 is in frame 1 and page 1 is in frame 4. You can see this page 0, 1, 2 and 3. So you can see here page 1 is in frame 4. So page 1 is in frame 4. This is frame 0, 1, 2, 3 and 4. So you can see page 1, this page you can see it is in frame number 4. You can see here. So from this we will understand which page number, which pages are in which frames. Now after placing the pages in the frame numbers, now the logical address will be created, means logical address will be there. So for logical address, in this example we are taken here, see, size of each page is 4 bytes. So 2 bytes will be taken for logical address, and this 2 bytes means total 4 bytes will be taken for logical address. 2 bytes for size of page and 2 bytes for number of pages. So total bits in logical address is 4 bits. So 4 bits will be taken for to specify logical address. You can see this. So this is logical address. Whatever you see here, this is a logical address, and it is of 4 bits. 2 bits of size of page and remaining 2 bits for number of pages. Now you can see here size of frame. Similarly for physical address also you need to specify the how many bits will be there in the physical address. Even the size of frame is 4 bytes. 2 bits will be taken for size of frame and 3 bits will be taken for number of frames. Actually there are 8 bytes. So from that 3 bits will be taken for number of frames. So total bits in physical address is 5 bits. So physical address will be of 5 bits. So whatever you see here, it will be of 5 bits. Now this logical address has to be converted into physical address. Now suppose if you want to translate the logical address to physical address, for in this example we have taken page number 2. So page number 2 is placed in frame number 3. So which is our page number 2? 0, 1, 2 and 3. So this page number 2 is placed in frame number 3, which is our frame number 3. 0, 1, 2 and 3. So you can see here it is placed in frame number 3. Now the logical address has to be generated for this page. So it has taken 4 bits of logical address. So first 2 bits, it is of page size. You can see it is of page size, page number, it is of page number. 2 bits are taken, and remaining 2 bits is of instruction number, which instruction it wants to execute. So remaining 2 bits it is of instruction numbers, this. So this is the 4 bits of logical address. First 2 it is of page number, and remaining 2 bits of instruction number. So CPU will generate logical address. So the CPU wants to execute the page number 2, and from that a particular instruction. Now to generate the physical address, it has to be translated in the physical address. So it has to be added with the frame number. So the instruction number, it has to be added with the frame number. So what is our frame number? So this is the address of frame number. So this is the frame number, and this is the instruction number. When you add this together, a physical address will be generated, and then the CPU can execute this page. So like this way, the logical address will be translated into physical address by adding this. So first of all, CPU gives the page number and instruction number, and then the instruction number will be added with the frame number, and then physical address will be generated. You can also see in this diagram, this is the logical memory. The CPU generates page number and instruction number. We also called it as offset. And whereas in a physical memory, frame number will be added with the instruction number, and then you will get the physical memory. Physical address you will get here after adding. And this is what? Logical address. And this will be having some specific size like 4 bits of logical address it can take, and it can be also translated into physical address. So it is based on the type of operating system. If it is a 32-bit, different logical address of bits it will take. If it is a 64-bit, different logical address size will be, physical address size will be there. So in today's topic, we have studied about non-contiguous memory. In that we have studied linked list using pointers technique and paging technique. In the next topic, we'll see some another new topic. Thank you.